Okay, this video is to show some kind of odd results I get from experiments using magnets to make electric currents. Very small ones, but it's odd. I've shown before using electric coils to where depending on which way you energize a coil and depending on which way it's wound is how you get a north and south electromagnetic field. And that's very explanatory, using an electric current to get an electromagnetic field and showing or displaying which is north and south. Okay, but the first thing I want to do here is show my magnets are coordinated, colored right. The blues are the south, the reds are the north on all of them. And it's just going to use these two, that bar magnet, or cylindrical magnet, and this round one. Spherical. The red is north and the blue is south. So I wanted to set that up first, and then just remind you, you can go back to a lot of my videos and see a lot of what I'm explaining up to the experiments. But electric coils are easy to determine north and south depending on which way the coil is wound and which way you energize it. Left or right winding, and you'll get a reverse north or south if you energize them from the same side, depending on which way they're wound. I've got a video that shows that too. But this is similar but different because it concerns magnets making electric currents. And we'll move on. Okay, I've shown in other videos, and you can go back and look, using this big wheel. And I've made a smaller wheel, which is the same. The arrows are oriented the same. If you look at a magnet this way, according to a CRT and similar TV screens, and even when I used an electric arc, the results of those experiments showed that there's a rotation to a magnetic field, and it rotates as you're seeing here. If you look from the north, it rotates counterclockwise, okay? And if you look from the south, such as this, it rotates clockwise when you're looking at the south, like that. All magnets do this. All it is which way it's rotating from which end you're looking tells you which pole we call south or north. So you can go back and look at my videos using this wheel and a TV screen, and this wheel and electric currents, or arcing electric currents, which shows or displays that's the way the rotation of all magnets seems to be. And that may be part of this problems of the results of the experiments I'm going to show you may be what I'm going to call is compression. It's acceleration, but the acceleration also causes compression in the dielectric. So I'll get to that later, but now we'll move on to the coils. Okay, what I've got here are two independent coils, and they're each hooked to two independent voltmeters. Turn these on, it's 200 millivolts. Oops. Okay. The coil on the right is red, so the red coil on the right is wound right-handed or clockwise, okay? The coil on the left is black and it's wound left-handed or counterclockwise. They're opposite. This is all independent. The red to the right coil wound clockwise goes to this meter. The other black coil wound counterclockwise goes to this meter. Here's my magnet. So with the south away from us, the north towards us, the rotation of the magnetic field is like the wheel back here. It's rotating counterclockwise. So what I want you to notice is the negative or positive bars on these. I'm not too much worried about the numbers. What I want to know is on the far end of the coil, the wires go to the positive. Both coils, the far end goes to positive, then closest to us goes to negative. So on either coil, if the charge is moving away from us, we'll get a positive reading. If the charge is coming towards us, we'll get a negative reading, okay? Pretty simple. So I'm going to do this several different ways. So if I lay the magnet in this coil on the right-handed, the magnet's rotating the opposite direction that the coil's wound. But if I push it in I get a positive reading. You have to watch the bar over on the side. If I pull it out, it'll be negative. If you see that. It's not so much how much juice, but is it going this way or that way, towards us or away from us? So when I push the south in, the charge went away from us, positive. When I pull the south out, it comes towards us, negative, okay? And that doesn't make sense to me because the magnet is rotating counterclockwise, but the coil is wound clockwise. It's reversed to me. I'll do it again. Push it in, positive. It went with the motion of the magnet. Pull it out, negative. It went with the motion of the magnet, even though the coil is wound opposite direction of winding that the magnet is rotating. Now, if I go over here to the negative, or the black coil, this is wound counterclockwise, watch this one. I push it in, I get a negative. It came towards us. If I pull it out, I get a positive. It went away from us. I'll do it a couple times. Push it in, negative, came back. Pull it out, positive, the charge went away. It's reverse. The magnet didn't change direction. We're still rotating counterclockwise, but these two coils show opposite directions of flow according to which direction the motion was. On this one, in is negative, which is opposite. Out is positive, which is opposite. On this one, in is positive, which is the same. Out is negative, which is the same. What I mean by the same is the direction of motion of the magnet is the same over here, but the rotation of the magnet and the direction of the winding of the coil is opposite. Over here, the rotation of the coil and the rotation of the magnet are the same, but the motion is opposite. I hope you see. Now, what's odd about this, that's inside the coils. Now, on the outside of the coils, it reverses. If I push in, I get a negative reading. If I pull out, I get a positive. That's on this one. Let me do it again. Push, I get negative, reverse. Pull, I get positive, reverse. But on inside, push, I get positive, same direction. Pull, I get negative, same direction. And out here, same thing is reversed. I push, I get negative, reverse. I pull, I get positive, reverse. Over here, it's the same, but it reverses again. If I push in, I get a positive. It goes with it. If I pull out, I get negative. Over here's the same. I push in, I get positive. If I pull out, I get negative. But inside, it's reverse. If I push in, I get negative. Pull out, positive. So the outsides are the opposite than the insides with the magnet in the same orientation with both coils, even though one's wound left-handed counterclockwise or the other one is wound right-handed clockwise. The motion of the magnet reverses inside or outside of both coils, but they are opposite of each other inside and outside. The other odd thing, if I turn the magnet around, I'm going to turn our wheel around. Now we're rotating clockwise. Everything we just did is going to reverse again. If I put the north in and push, I get a negative reading. It came towards us. If I pull the north out, I get a positive. Okay, I guess you've seen that. Push it in, negative, pull it out, positive. And it reverses again on the outside. Push it in, positive, pull it out, negative. Push it in, positive, pull it out, negative. And over here, it's exactly reverse what it was a while ago and reverse to that one just now. Put it inside, push is positive, pull is negative. Inside again, push is positive, pull is negative. And the outside will be the opposite. Push is negative, pull is positive. Well, I didn't show. Push is negative, pull is positive. And the same over here. Push is negative, pull is positive. They're completely reverse of each other. The same motions with each end and reverse of each other again with the same motion on opposite ends. And inside and outside is reverse. And we can do the same thing again. What we just showed on this side, let me do it this way. I'm going to go back to the beginning. If I put the south inside and push, I get a positive on the right-hand coil with the magnet rotating counterclockwise in the clockwise winding. I pull out, I get negative. Push in, I get positive. It follows the motion of the magnet. But if I keep the magnet in the same orientation and I go to this side of the coil, when I push towards this, I get a positive. It went the wrong way, opposite. And if I pull out, I get a negative. It went the opposite way. With the magnet in the same orientation, like this, depending on which end of the coil I'm on, it reverses direction. On this side, it'll show positive with it. But if I put the north on this side and pull it out, it shows a negative. It's reversed. This does the same thing. If I put the north in, positive. North out, negative. Now I'll leave this in the same orientation. South in, positive. South out, negative. It reverses. So it reverses, and it does the same thing on the outside, the inside, back here as it did in the front. It all reverses. Every orientation of inside to outside reverses, and left and right windings reverse, and pole reversal reverses all that. And even with the pole in the same situation, it reverses again on this side. So there's something to the way the magnet draws the dielectric into itself through the coil that's causing that to happen. So I've got some more experiments I'm going to show you on the same exact subject, and we'll do that next time. So give me your thoughts on this. Why does that do that? Laters.